Yeah, so following up from that intro, I'll just get right into it. The talk is a summary really of techniques um, and problems that you face when auditing protocols, especially more complex stuff. And I'll go through not just the, hey, I mean, like what happens when you go through the code, but like the game theory side of things as well, lightly. So what's an audit concerned with exactly? So they're not just for finding bugs. If you just want to find bugs and reward for that, you get a bug bounty. But an audit really is meant to analyze the soundness of the project's design as a whole, on top of current and future security, right? So just because like the code base as it is right now as a static element may not have anything critical, um, it may be structured in such a way that it is easy to make critical mistakes on further evolutions of the protocol, right? So it's kind of a holistic thing. Not just the code, but how people interface with the code, how they interact with the code, how they think about the code, sort of everything related to it. And so to be able to evaluate design, the most important thing is to have a specification available, because otherwise I don't know what I'm supposed to be auditing. You don't know what you're having audited, and nobody really knows what the thing is actually supposed to do in the first place. We all kind of we just like end up operating on a set of assumptions that we are not even sure that we really share. So that's really important. Just the act of writing down a specification often helps you find issues or mitigate or prevent issues that would have come much longer down the line and in much less obvious ways and also much more complicated ways. So it's not a very common thing in software engineering discipline to write specifications, at least not to the extent that they are written or sort of handled in other disciplines, like, I don't know, mechanical engineering. Normally you don't just start throwing iron beams into a lake until one of them lands in the right way. You research materials design and the right junctures and make sure the bridge doesn't collapse, the moment a truck steps onto it and stuff. That's not very respected in software just because software is cheap, and there's a disconnect between making a mistake and someone feeling that mistake. So, versus like if a bridge collapses, that mistake is pretty evident immediately, and the damage is evident immediately. But nonetheless, it is a very important part of software design, and really everyone should upskill themselves in at least being able to write, like if not formal specifications, at least some kind of specification. One of the tools that I use when doing more complicated when trying to understand more complicated protocols is something like Alloy. So Alloy is just in a class of formal modeling tools or relational modeling tools. There are a few different things, like Isabella Cock, Alloy. Sometimes it's more on the formal verification side, somewhere is on the specification side. But when you are talking to your coworker or whiteboarding a spec, you are talking to another human and you are communicating intent, right? And that's very different for programming. Programming is not, when you're programming, you're not communicating intent to the machine, you're encoding mechanism, right? So I think that's also like a huge source of bugs, which is thinking that because you've whiteboarded something with an employee and none of you have found bugs because you've both kind of assumed that the intent is correct, that now when you go to implement it into a machine, that you're less likely to have a bug because the intent has been ironed out. But the machine doesn't really care about intent. Your machine just cares about what you're declaratively specifying the mechanism is, right? And that's why languages like this help a lot, because it's kind of like I like to call it computer-assisted program design. Kind of like you have computer-assisted design for creating in CAD, creating, I don't know, bridges. I'm not a mechanical engineer, I don't know what they really do, but I'm sure it helps instead of just trying to imagine what the bridge looks like. But this is sort of the equivalent for programming. You go through, and the language is probably unreadable for anybody who has never done this before, but there are just basically set relations and relational axioms, and saying, the set of names should have at least one address, and the relations between names and addresses should be one. So it's basically, this is just implementing a linked, this is a specification for more or less an address book, linked list, right? And then you can run these tools allow you to check your design as well. They will evaluate the designs, try to find counterexamples, or say, oh, this is a linked list, and you implemented, like, your linked list does not respect idempotency, right? So if you delete an item and re-add the item, there's like an orphan node, and that node can actually end up having two references, just because you were thinking about intent, but you didn't think enough deeply into the mechanism, right? So that's one tool I think. Alloy is a pretty easy one to pick up, but it's something that really helps. Even if you learn how to use it and never actually use it, it's still massively helpful to have to experience the disconnect between mechanism and intent in your mind for one time. Also, another one that I often use when doing very complex code analysis. Smart contracts are getting more and more non-trivial. They are relying a lot more and more on moving components, and so it is helpful to have a static code analysis tool, just to at least to be able to answer quickly questions about the code base, to say, show me I want to see at a glance all the functions that change state. So this is a screenshot from a tool that I've personally written. There are similar ones on, if you just Google, static analysis Ethereum. But say, okay, here's all the functions in blue, all the internal functions in blue, all the external functions in, I don't know what the color is, beige. What accesses state, what modifies state, and I can see, all right, this code base is a mess, or this is where I should focus, whatever. Where are the interfaces? How many moving components does this rely on? And I think this is also outside of cryptocurrency, just in the industry as a whole, massively underrated. Humans have really powerful visual processing, and it actually, like, reading code line by line is not a very good way to quickly understand the structure of the code base. So if you have, in whatever language, if you have a static analyzer that can create a picture of the code base for you, it is immensely helpful to have something like this to refer back to, instead of trying to remember how many functions call this function, how many levels am I deep in this stack? No, just use your like massive visual cortex to have like a reference point. And then also one of the main things is experience in auditing. Just like there are design patterns in programming, there's exploitable patterns in security analysis. You have as you get better and better in programming, you see the same things. Oh, whatever you're doing, whether it's network programming or a database or whatever, there are like higher order functions you can abstract away. There's categories of functionality that everything comes like fairly similar, and you have these little puzzle pieces that really only the edges differ. In security, it's the same thing. The more code bases you look at, the more you realize everyone makes the same mistakes in almost all the same cases. There are things humans are very bad at. Like things that are state machines, like very deeply nested state machines. You very easily lose track of where you are in the state machine in your head and start assuming bad things. Anything that deals with like a lot of indirection, arithmetical indirection. So in my C days, before smart contracts, that used to be like pointer arithmetic, or very deeply nested pointer arithmetic, array indexing. People always get that wrong. Encoding, decoding, multi-step protocols. People are overconfident in their ability to manage complexity, and you can always bank on that. Humans are fairly overconfident in general, and they're like in their own ability to manage complexity. And unless you have sort of really learned to be very careful in certain domains, you're gonna make these mistakes, and they're fairly repeatable. And this only grows the more people that work on a certain project. If somebody else has written a set of functions and has named them wrong, or has named them in a misleading way, where the function says calculate x, but actually while it's calculating x, it updates a state variable, you're just going to use it and assume that that is not changing any variable, and then you might call it multiple times and cause a incoherent state. So bad assumptions and overconfidence are like a thing you can always count on in very large code, in most non-trivial code bases. And there's also like a whole other side of auditing, which is the game theory side. And on the game theory, like one of the better examples for how a protocol is designed. There's non-obvious properties of protocol design that only show up very later on down the line, which is like an example of Freenet. So Freenet is a network from the pre-cryptocurrency days. It's like it's a distributed network. It's decentralized, blah blah blah. But there's no cryptocurrency, so there's like no incentive mechanism for making sure that like people are running a certain the protocol in a certain way, or contributing to the network in a certain way, or maintaining it at all. And so Freenet, like in short, is a distributed file storage protocol. So I download a Freenet client, you download a Freenet client, whatever. The more I allocate to, the more I give the client in terms of like space on my hard drive as an allocation, the more that I can allocate to the rest of the network. Again, there's no incentive design here, so it's kind of like a promise. But it's so if I can say, look, I have 50 gigabytes available. So people will send me encrypted chunks of data, and then equally I can send people encrypted chunks of data, and this data is just referenced as an IPFS hash would be referenced. It's actually very close to IPFS, except for it's just meant for large files. So the more a file gets requested in the network, the more nodes start to store it. The less it gets requested, it moves down the queue and eventually just drops off the queue. And so strategy of the commons is kind of it's one thing that happened on Freenet because it kind of shows the power of the faults and like uninformed participants. So what a explanation of strategy of the commons is basically airplane seats. Like if you're on an airplane seat and you're like reclining, it's a benefit to you, but it's bad for the person behind you. And then that person will also recline, and it's like a chain effect, right? The only person who isn't reclining is the one that is the only person who can break that effect, but they're like everyone else is in their face, right? So this is basically what happened in Freenet. Somebody made a client that broke the symmetry between upload and download, so it would only drain bandwidth from the network. It would advertise that it had a lot of bandwidth, but it would just never store anything. And so everybody would, if you use this client, you wouldn't need a big hard drive at all, but your network experience was amazing, except for whoever did this released the client, everyone started using the client, and the network went down. Because of course, the moment no one's uploading, the network doesn't exist anymore. So I think this is a lesson that you have, it's a hard lesson to learn in cryptocurrency, because if there's a much more value attached to it, but there are a few protocols that have a strategy to commons element that just hasn't surfaced yet. As another one, you can have game theory incentives, like you can perverse game theory incentives, right? So as an example, maybe I like the Monport protocol, but I just want to change a few things because I feel like I'm pretty smart. So I'm just going to fork the network, change the name, and change a few things. So maybe you can say, oh, right, you can have users, they invest in funds, and those funds hold shares, but the shares are not transferable. I don't really like this about the Melon protocol, because, I don't know, maybe I want to create a system where funds can invest in other funds or something, like a fund of funds, like a S&P 500 for digital assets. So, I create an extension of the protocol where actually you can do this regardless in most systems, because most protocols don't catch this. But I'll create an ERC20 shareholder contract where I pay money to this ERC20, the pink contract. That contract forwards the money to the fund and takes a share entitlement, and then just keeps an ERC20 map of holders. So now I allow holders to buy these shares through me and transfer them, and I've broke. Even though the fund itself does not allow share transfers, I have gotten around it through an abstraction. So now these users can trade shares between each other without going through the fund. I mean, it doesn't really give you that much. It doesn't really give you that much benefit in this case, because why would you buy from this third-party contract versus buying from the fund directly? However, maybe I also removed the whitelisting factor from the protocol, so then the fund can invest in whatever the hell they want, and now the fund sees a new asset rising in value, and so decides to start holding that asset, and the fund purchases ERC20 shares of this holder contract, and that becomes part of its holdings. So the fund now holds a token that represents shares in its own fund. And so like either the fund's making value out of nowhere, or it's massively over leveraging itself, or something about the fund equation breaks here, right? Because you shouldn't really be able to buy the S&P 500 shouldn't be able to buy part of its own index as a part of its index. It doesn't make any sense. So, and this seems like a silly example, maybe, a mistake that can come from wanting funds of funds, but there are far more non-trivial nested examples of this. There are many margin lending platforms now on Ethereum. There are many, collateralized debt obligation platforms. You can imagine a scenario where, or like whatever, baskets of asset platforms. You can imagine a scenario where unknowingly people end up having this self-referential chain of asset holdings where the margin lending protocol relies on the performance of a fund, which holds some like derivative, which is based on the asset held, on the margin lending platform. And then you have like the crypto equivalent of 2008 situations where once the volatility reaches a certain point, the entire house of cards collapses. In the normal world, let's say in the non-crypto world, these things like Dodd-Frank regulations prevent kind of some of this stuff from happening. Not all of it, but derivatives are a bit more regulated. But where people can get creative without limitation on smart contracts, and people don't want to write specifications, it's easy to get into a very complex scenario like this without realizing it. So, in conclusion, just 20 minutes past, security and correctness of a design are not just itemized lists to check off, but have to be a conspicuous part of the entire development process, from conception to delivery and beyond. And in new domains like smart contracts, the set of possible interactions between systems is unintuitive. Like if you really think that you understand smart contracts entirely, you don't really understand smart contracts. So exploits can be too deeply nested to be caught from surface level reasoning. It's a domain that enables sets of interactions that just do not exist otherwise, just because of the autonomous nature of these agents or assets or events or whatever. So that's it. Any questions?
Is there any questions on this?
How do you usually run
just 1 second.
Security, let's say, threat project? Sorry. How do you usually run let's say, a security assessment project?
So it depends on the project, but first definitely analyze potential sources of issues. What does it depend on? Does this network depend on Kyber? Does this network depend on DAI existing? What are the issues with that? There are, again, are there game theory issues? There's code issues, the complexity. What is the impact? What is the exposure level of the users if they interact with this? What's the exposure level of the managers? And you kind of try to minimize each category and try to prevent. So my approach to security is always, I don't try to fix individual issues. I try to prevent categories of issues, because then you mitigate stuff that you don't know about, which is much better.
Thanks. Is there any more questions? Oh, there's one back there. All right.
What's your take on upgradable contracts with regards to trust? And I mean, on the one hand, they can provide the ability to fix the contract, which is nice, but on the other hand, they kind of break this whole trust assumption. So,
well, I mean, in a way, it's kind of necessary, right? It's difficult for non-trivial stuff that you're going to get it right up ahead of time. So they're necessary, and of course they erode trust to some extent. Maybe you can have a multi-sig that's never upgradable, and that's fine because you have a set. But the network evolves. You may want to eventually evolve your smart contract. So I think it's a necessary evil, but you want to minimize the impact that the upgrade has.
Cool. Thank you for your talk.
Yeah, no worries.
All right. Let's give him a hand.